All right, so welcome everybody to EE290C. So as you can tell, hopefully from the slides, and many of you, I guess, guessed just based on what I generally work on, this class is, even though it's called Advanced Topic in Circuits Design, in particular what we're going to be talking about for this semester is essentially high-speed interfaces, and in particular circuit design for high-speed interfaces. So I think most of you guys already know me, but just in case if there's people out there in the universe watching this on the webcast, my name is Alad Alan. I'll be the instructor for this semester. So just as sort of I've started talking about already, what this class is really going to be all about is really going to be circuit design for basically these modern high-speed interfaces. Okay, and so I sort of put in blue and underline circuit design here because my intent really is to focus on sort of the deep circuit building blocks of how you actually put these interfaces together. So having said that, I really need to sort of just put something in the context though. So but as you'll see by the end of the class, these interfaces are actually becoming pretty complicated mixed signal communication systems. So what that means is that even though we'll be doing a lot of transistor level design, in reality you really can't just go around hacking on transistors and then expecting that at the end of the day you'll get the right system. Okay, so we will spend a lot of time talking about what are kind of the system level requirements and even just how you'd go about designing the systems to make it so that the circuits you build actually make some sense. Or perhaps even, say that a little bit better way, so the circuits will actually end up being optimized for what it is that you're trying to do. Okay, so really the goal here is essentially to figure out what is it that we need to know and essentially what are the techniques that we need to be able to apply in order to design a high-speed interface for some given application. Okay, and what I mean by application will obviously become more clear as we go throughout the semester, but you can imagine there's a lot of different places where these interfaces sort of pop up, and depending upon how exactly they're used and what are the requirements in those particular contexts, that may drive you to build the circuits in a very different way. Okay? So just as usual, a few sort of administrative things. Obviously the class is being webcast, so please try and speak clearly when you ask the questions. I may repeat the question just so for the benefit of the people that are watching online. The fact that it is webcast, of course, tends to mean that we won't necessarily get a full house like we've got here today. That's generally, let's say, okay, but as most of you guys know, I try and keep things very interactive. And if I start seeing that the numbers are dwindling steadily at an exponential rate, so that we've only got 1 or 2 people left in a week or so, I'll take some drastic measures, like come to your house and knock on your door, or delay the webcast by a couple weeks or something like that. Okay, so bottom line, I know it's late in the afternoon and it's sleepy time and all that, but please do try and be here because I promise I'll try and keep it fun and exciting and all that, so it'll be worth your while. Okay, so other than that, again, as I think most of you know who've taken classes from me before, the website is kind of the main place to go for everything. So all the homeworks, all the announcements, everything will be up on that website. So I've given the link right here. If you just sort of search for EE290C Berkeley, you should also find it. Or alternatively, if you go to my homepage, which again should be very easy to find just by Google searching for me, you should be able to get here. But you've got the notes now, so if you're in doubt, that's where it's at. The webcast is just in the standard webcast, .berkeley.edu. So go take a look there. In terms of office hours, that'll just be in my office. On Tuesdays, I'll hold it from 9 to 10, and on Thursdays, I'll hold it from 11 to 12. And obviously, if you have questions or things like that you want to meet, just send me a note. I'm happy to get together. There's no, let's say, GSI or reader right now for the class. There definitely won't be a GSI. I may manage to twist somebody's arm to be a reader. But given that most of you guys are anywhere from 2nd to 5th year graduate students, there's not that many people in ICs left who I could hire as the reader. So you may be stuck with me doing the grading. But anyways, we'll figure that out as time goes on. And as I mentioned before, all of the announcements for the class will really be made through the webpage. So make sure you check back on that often because I won't, broadcast emails or anything like that unless it's really something, urgent and critical. Otherwise, just go back to the web and check things out over there. Okay. So, just in case, people sort of weren't sure what it takes to kind of do well in this class or what I'm sort of expecting from a knowledge standpoint. So the bare minimum from a sort of prerequisite standpoint is basically EE141 and EE240. Now, it just so happens that, those are classes I usually teach. That really has nothing to do with it. That's just, kind of material-wise what you need to know. By the way, EE241, if you've taken that, would certainly be useful, but not necessarily required to sort of do well and understand what's going on in the class. But 141 and 240, definitely I sort of expect that you'll know that stuff. Now, there are sort of, let's say, slightly different flavors of 240. So some people may have taken 240, for example, from Bernhard or from Ali a few years back. And actually, just to sort of get an idea, I think I know for most people, but who here didn't take 240 with me? Okay, so you should still be just fine. There's a few things that I may have covered in 240 in the version that I give, just because the high-speed, the project in that class, I usually make a high-speed serial link. But I'll try and at least give you the basics of what I expected people to learn from the 240 stuff, even in these lecture notes. And the good news is the 240 stuff is all webcast as well, so you're free to kind of go back and take a look at that. But as long as you've had some version of 240, you should really know everything that you need to know to do this class. There are a few things that I'm going to sort of assume that you're at least vaguely familiar with or you've heard about before. So first, I'm just going to assume that kind of basic data converters, so comparators, flash ADCs, maybe even slightly more complicated types of things you're familiar with. Similarly, just basic digital to analog converters, and that's actually probably more important. I'm also going to assume that you're sort of familiar with that. Now, that's not to say that I want you to design, the latest record-breaking figure of merit, 0 femtojoules per conversion step ADC. It just means you should sort of be familiar with those things and kind of, for those of you guys who took it, at the level of like the EE240 project that we did with a high-speed serial link. Okay, so even 247, if you've taken it, great. If not, that's fine. You should still be able to do just fine in this class. The other thing I'm just going to assume you have some level of familiarity with is Verilog or VHDL or some other essentially RTL type of language or hardware description language. And the reasons for that will become a little bit more clear later on. But in the context of the project, if you're familiar with that, it'll help you just to sort of get ramped up a little bit more quickly. Okay? The last thing that I'm going to assume that you just at least have seen at some point before is kind of basic transmission lines. So I'm going to assume you sort of know what a transmission line is. You know why there's reflections and things like that. I'll talk a little bit about it maybe actually next lecture, but at the very basic level, I'm going to assume that people know what that is. And I think in Berkeley, it's only really EE117 that covers that. I could be, well, okay, I talk about it a little bit in 240, but maybe just to sort of level set, is there, well, okay, who here does know about transmission lines, or at least has heard of them before? Okay, great. So I don't need to say too much more about that. Okay. Last thing is that if you have some exposure to either sort of communications or some degree of signal processing, that will also be kind of helpful. Now, again, this is not that I want you to be writing, theoretical proofs of, any theorems or anything like that. It's just, having some familiarity with those things will help you in terms of just understanding the concepts that we'll be talking about. So, again, no deep expertise is required there. I'll really cover sort of the important points in the context of what I'm interested in. But if you've seen that stuff before, obviously, it's much easier to kind of appreciate what's going on. Okay? Any questions on sort of just material kind of stuff, or are we good so far? Okay. Okay, so again, sort of as usual, for those of you guys who have taken classes from me before, the main sort of source of material for this class will really be the lecture notes. And what I mean by that is not just sort of what's written in the slides themselves, but what we actually talk about in lecture. Because you'll see that I'll make use of the tablet. I'll oftentimes give you slides that are just blank, and then we'll write them in together sort of in class. Okay? Now, I should mention that a lot of the material is going to be drawn from not just myself and my own knowledge, but from actually courses that have been offered both here at Berkeley and at other institutions in the past. So a lot of these slides are taken from Bora Nikolic, from Vladimir Stoyanovich at MIT, and from Jared Zerby, who's been at Rambus, and actually offered the 290C course, I believe, the last time it was given, which was about 7 years ago or so. So basically, I'm taking a lot of material from those, and of course also synthesizing it with kind of new stuff that I want to focus on. So again, this is really the primary source of material for the class, so there's no required reference text. I'll tell you a little bit about a couple of texts that you can kind of go to maybe get some more information from, but really the core is these lecture notes. And I'll do my best to sort of post it on the web at least an hour before the class so that people who want to can go ahead and download that ahead of time, or get yourself a tablet and write things on that instead of the lecture notes and things like that. So just actually on that note, how many of you guys actually want printed copies? And I'll try and save some trees, but if you want them, that's fine, no problem. Okay, so basically everybody. So I'll just sort of do some binary search in terms of getting the right number. So occasionally you may not get one, but I'll converge on that fairly quickly, and I'll make sure that most people have the hard copies if they want them. Okay, so as I said, the lecture notes are really sort of the name of the game in terms of the class material. And in fact, a lot of the stuff I'm going to be talking about doesn't really exist in any textbooks anywhere. But I also know that a lot of people just like to go back and sort of read things and learn things a little bit better that way. So because of that, I've given you just a few example references here. So the first one is this Digital Systems Engineering book. This is by Bill Daly and John Polton. It's kind of getting a little bit outdated now, but still a lot of the basic ideas are obviously there. And certainly in terms of just the breadth of what you need to know about, just a lot of the basics are certainly there and worthwhile taking a look at. The other sort of, let's say, it's not really actually a book, but let's say piece of a book that's worthwhile is this Design of High-Performance Microprocessor Circuits. Not because we're going to be building processors, but because there is a chapter on high-speed interfaces inside of there. And it's pretty well written, again, slightly outdated, but gives you just some idea of what kind of the basic issues that we're going to be talking about are. The other one is this Razavi book about design of integrated circuits for optical communications. We may talk a little bit about optical towards the end of the class, but it turns out, and for those of you guys who work on optics, I'll apologize in advance. Turns out most optical links are basically electrical links with junk bolted onto them. So if you understand, kind of what that is, on the back ends, then, even though we're focusing on electrical links, like you'll get a lot of the same idea. Okay. The other thing is we will spend some time just looking at, not necessarily looking, or I may refer to various papers from different conferences, different journals, and etc. Most of them from sort of IEEE solid state circuits kinds of things. But I'll try and give you the references on the slide, and I may also sort of collect a list of those papers on the website with like a link to IEEE Explore if you want to go take a closer look at those. Okay. Okay, so let's say the practical question that I'm sure everybody's interested in is just, well, okay, great, this sounds interesting, but what's it actually going to take to do well in this class? So, the bad news is I do have to grade you one way or another, just because that's sort of how the university works. So the way I'm going to do that is basically 30% of the grade will be from the homeworks. And it turns out I'm only going to do maybe 3 or at most 4 homework assignments. They will be fairly substantial because they are, as you can see, a sort of good part of the grade. And more importantly, I'm doing those homeworks not because I like giving homeworks and I like grading them. It will be very useful for you to learn the material in the class. Okay, so I promise if you do the homeworks, it'll be worthwhile. It won't just be a bunch of grunt work. Like I'll try and make them actually pretty interesting and directly relevant to the things you'll be dealing with later on. Okay. So as you can also tell, the vast majority of the grade here will be actually coming from the project. Okay, so the project will basically be looking at really building a complete serial link. So many of you guys sort of got, let's say, a little bit of a flavor of that already in 240. But when I say complete, I really mean complete. So all of the stuff that I said in 240 you didn't have to worry about, you're going to have to worry about this time. Okay? Now, don't worry, I'll tell you how you actually deal with all that. But it is going to be a substantial project. And I guess for those of you guys who've taken my classes before, you know that I really mean it. Like that really will take a lot of time. It really will require a lot of effort, but it'll be worthwhile. Okay, it'll be fun. You'll learn a lot. So hopefully you'll enjoy doing it. The other thing I should mention is that this, unlike in the past or unlike most of the classes, this will be a slightly larger group project just because of the sort of amount of stuff that needs to be done. So my expectation is there'll be groups of kind of 3 to 4 people. And because it does involve building the entire link, that means that you'll want a pretty, let's say, wide variety of expertise within the group. So even now, you may want to sort of start talking around with people and seeing, who you'd like to work with, because, getting a good group right from the get-go will obviously give you a great head start on really getting things done later on down the road. And as I had mentioned, actually, or as it's written on the slide here, we're actually going to do a pretty high-performance link. So I'm shooting for something like 10 gigabits per second plus. That's not because I'm mean. That's just because if you sort of, if you were to go and get a job today in the industry, pretty much you'd have to be working on something in that range to make it really kind of worthwhile going after. Okay, so that's kind of where I chose that from. I'll obviously give you a lot more details as we get closer to that, but that's kind of, just to give you a heads up. The other sort of, let's say, last 10% of the grade will be on essentially presentations that you guys are going to give. Now, those aren't just going to come out of nowhere. They're actually going to be directly related to the project. So essentially what I'm going to do is I'm breaking the project into actually several different stages. I believe I've got it in about 4 different stages right now. 2 of those stages will basically have you giving presentations on them. Okay, so there's sort of 2 purposes for that. One is I think it's really important to just learn sort of how to communicate your ideas and how to communicate just what you think is interesting in what you're working on. But 2, I've broken it up into that many pieces because since it is such a big project, I want to make sure you guys are on track in terms of getting things done. Okay? So basically, the first presentation will be at kind of like the project quote-unquote halfway point. And again, I'll give you some more details as to what I expect there when the time comes. And then the last one will be sort of kind of like summarizing your overall final project, and of course also giving some opportunity for other people in the class to provide feedback or ask questions and so on and so forth. Okay? So the last, let's say, piece of good news for all of us is there won't be any exams. Okay? So no midterm, no final, nothing like that. But that's not to say that this will be a party course. Okay? Because as I said, the project will definitely take a lot of time. The class overall will definitely be sort of a pretty intense class. I'm intending to make this, much more of, let's say, a 240 style class rather than a seminar where I just, bring up random topics and sort of talk about them for 50 minutes. Okay, so the really sort of, let's say, hardcore material here. So you should plan accordingly in terms of just budgeting time and making sure you get everything you can out of the class. Okay? Any questions so far? Or? Okay, good. So this is just sort of the standard stuff. Homework, you're free to discuss and work together with other people, but you have to write up your own. I'm not even going to mention cheating here because hopefully if you've gotten to this class, you've sort of realized that that's just a waste of your time and a waste of everybody's time. So feel free to talk to everybody, feel free to work together, but just turn in the actual work by yourself. Just put that outside my box. It'll generally be due on Thursdays, but the exact times and everything will be posted up on the web. And again, as usual, there won't be any late submissions because I'll basically do my best to actually post the solutions fairly shortly after the homeworks are due, so that again, you get a chance to go and sort of take a look at what you were expected to do, what made sense, and so on and so forth. So again, as usual, make sure you start early on those things because they will indeed take some time. Okay? Okay, so just a few notes, which again should sort of be fairly expected for most people. I assume that just about everybody here will be at ISSC that week. That includes me, so we won't have any lectures. Okay? So you get to, let's say, go party that week. We'll have spring break, of course, which obviously also has no lectures. That's kind of towards the end of March. And then in terms of the project, as I said, that'll be split into a few different pieces. So definitely, take a look on the web for the updates on that. We'll be starting on that fairly early on because we only have like 3 or 4 homeworks that we'll be doing. The first presentations for the project will be kind of roughly first week of April or so. And the final presentations will be during the 3R week. I forget exactly what the 3 Rs are, but basically it's during kind of like the dead week because I figured that'll be the easiest in terms of scheduling and getting everybody here and actually doing the presentations and all that. Okay, so any other questions on just logistics kind of stuff before I actually tell you, a little bit about why we're here and why this should be a fun class? You guys are too quiet. Okay, so why are we actually here? What's going to be going on in this class? Well, as many of you guys I think have seen before, if you kind of think about what an interface or as I usually refer to it as a link, all you're really trying to do is get a bit from the transmitter over to the receiver. Okay, so from a sort of 20,000 foot view, the simplest way you could think of to do that is you basically just have, let's say some flip-flop or whatever timing element it is, some driver, which could even indeed actually be an inverter. You send that over some wire, and then on the other side, you have, again, some inverter and some flip-flop that just, let's say, retimes the data. Okay? So turns out this really is a link. Okay? This really is a interface. It may not necessarily be a high-speed interface, or it may not be the best way of building an interface, but this really is an interface. Okay? So kind of when if you sort of look at it that way, you say, well, okay, this should be really easy, right? I mean, we learned about flip-flops and inverters in 141, and a wire is just a wire, no big deal, right? So why are we even bothering to have this class, right? What's going on? Okay, well, let's actually take a little bit closer look at where links are actually used and sort of why people, let's say, are even working on these things in the first place. And I think we'll pretty quickly figure out why, maybe life is not quite this easy. Okay? So I think many of you have sort of seen this slide before. I apologize that in terms of the printout, it doesn't look that great, but hopefully you can see it here on the screen. If you sort of think about what's happened over the last few years, and maybe this has actually been happening over the last about 15 years or so, every time you get that new iPhone and you start, Googling or YouTubing or whatever it is you do on the go, those bits have to fly through somewhere, right? Because even though they went through the air and, got to the base station, that base station has to go and grab that web page from wherever the heck in the world it is that you were trying to talk to, okay? So if you actually looked even just inside of the United States, there's this huge network of essentially what's called backhaul links that are just communicating between these different, let's say, sort of hotspots or server centers in the world that are really forming what the internet actually is. Okay? Now, if you actually go and were to look in, let's say, one of those big, backbone router or big backbone kind of locations, you'll see one of these pretty big boxes kind of sitting all over the place. Those big server rooms where we see all those computers actually doing stuff. Turns out not all of those things, not all of those big racks are actually computers. A lot of them are what's called these routers. Okay? So this particular one, I actually don't know how big it is, but ballpark, we're talking 3-4 feet on a side. Okay, maybe even more than that. Okay, and this whole thing could actually be dissipating order a few kilowatts. Okay, so the only purpose of this little rack here is just to get me over here in California talking to, I don't know, my buddy over there in Boston or whatever it is. Okay, it's just making those links so you can actually get across the entire country for that, couple of bits of image that it was that you wanted. Okay? So as we'll see, actually, inside of these things, and in fact, even in between those boxes, that's where these kind of high-speed interfaces are going to be used. Okay? Not only that, of course, even if you looked inside of like your own computer or let's say your own console, even there's actually quite a few of these so-called high-speed links that are actually playing a pretty critical function. Okay? So kind of the meta message there is that not only is there a lot of data being pushed around all over the place, but basically these links are actually all over the place in all of the electronic devices that you're interested in. Okay, so if I looked inside of these backplanes, they actually kind of look something like this. You'll see a lot more pictures of these, so don't worry if it's not too clear as to exactly what's going on there. I'll describe that in 1 second. But even inside of your PC or your console, even just to talk from, for example, your CPU to the memory, turns out people want approaching terabits per second of throughput there. Okay, and so that means if you think about terabits, that's a lot of very high-speed links. Okay, takes a lot of effort to actually get those things transferred correctly, and to do that within some fairly low power and area and cost budgets. Okay, and we'll talk some more about that in 1 second. Okay, so let's actually take a look at sort of what goes on inside of one of these let's say backbone router kind of boxes. Okay. So this picture that I was showing you over here, this kind of really is what's inside of here. So this is just kind of a more cartoon version of it. So inside of that router, what you typically have is 8 to 16 so-called line cards. These are the things that sort of go out and talk to the rest of the world, meaning those links operate over like usually kilometers of distance, okay, or multiple tens of kilometers even. So on those line cards, you usually have some sort of optics. As an example, let's say an OC192 link. So the OC192 just means it operates at about 10 gigabits per second. So there's some sort of laser driver, some sort of transimpedance amplifier or photodiodes and so on and so forth kind of sitting here. That's again sort of going out over the long distances. Well, but if you kind of think about it, there's lots and lots of traffic flying all over the place, right? And so you want to be able to take one of these nodes or one of these backbone routers and route data from all kinds of different locations to all kinds of other locations, right? So basically what you'll typically do is between those optics and sort of, let's say, the rest of the system, you'll have some sort of what's called SerDes, which just stands for serializer, deserializer. So really all this is doing is taking that 10 gigabits per second data and putting it out in this particular example into 4 parallel lanes, each running at 3.125 gigabits per second. Okay? This is usually what's done with what's called a ZOUI serial link. Just like with wireless, there's a whole alphabet soup of wired links. ZOUI is just one of them. Okay, I forget exactly what this all stands for, but you can go and look it up. It just means this particular type of serial link. From there, you have to do all kinds of the media access processing, figure out, do the network processing, figure out where are these bits actually supposed to go, what's the actual other line card or switch card that I want to talk to, and then from there, essentially, you go out into sort of basically what's called this passive backplane. Okay. So the passive backplane, that's just this sort of big board sitting over here. Literally all it's doing is it's a whole bunch of wires connecting these different switch cards to each other, or these different line cards to each other, okay? And since I already mentioned it, you've also got these so-called switch cards. Usually those are the ones that you sort of would send all of your data to the switch card, and then the switch card would say, oh, okay, this data came from here and is supposed to go there, so it'll forward it over to the other line card to kind of make that full connection, okay? So on these backplanes, again, you can imagine there's sort of lots of communication you'd like to do back and forth. Each one of these is usually running at somewhere between about 3 and an eighth to about maybe 12 and 12.6 or 12.5 gigabits per second. Okay. So, by the way, I should mention this picture that I've drawn here is sort of circa 2006 or so. Okay, so maybe 5 to maybe even up to about 10 years ago, this was kind of like what a state-of-the-art backbone router would look like. And as you can imagine, what you really care about in these things is just how many gigabits or even terabits per second can you get sort of through the cross-section of this thing, right? Because that kind of tells you how many different connections can you make and how fast can you actually form them, okay? So to give you an idea of why, sort of this field is kind of interesting and evolving, as I said, this is kind of the picture of what we wanted to do circa about 5 years ago or so, okay? So let's look at what a backplane today, an interesting backplane today might need to do, okay? So as you may have noticed, like in terms of the cartoon, nothing has changed, okay? So I didn't change anything about, the line cards. I didn't change anything about the backplane. All I've done is taken pretty much every single one of those data rates and multiplied them by 4, okay? So instead of an OC192, now you might have an OC768, which is a 40 gigabit per second optical link, okay? Similarly over here, instead of having, those 3¼ gig links, maybe now I have to do 4 by 10 gigabit per second links, okay? Similar now out on these backplanes. Well, okay, now if I want to actually support that throughput, now I need to go up to, let's say, in the order of 25 or maybe even 28 gigabits per second on those backplanes, okay? So kind of the key point here is that, notice, I haven't added any extra cables, I haven't added any extra wires, and in fact, as we'll see probably next lecture, I probably even made only minimal changes to this printed circuit board, which is what I've called the backplane, but everything has to run faster, okay? So that pretty clearly means that, from a standpoint of us as the guys who have to build these links, somehow we just have to get better, right? Something has to drive us to be better. Was there a question there?
Yeah, so how much of that is just due to transistor scaling and how much is actual architecture changes?
Okay, so we'll talk about that some more, but as I guess you know reasonably well by now, transistor scaling unfortunately is not buying us as much as it used to, right? So there is certainly some raw speed issues, but actually, well, you know what? I'm going to answer that question in like 2 more slides. So if it's not answered, then ask me again. Yeah?
Another one. So what's the typical power breakdown inside the line card?
Okay, so that's a great question. So I think it's about 50-50 in terms of I/O versus processing in memory, ballpark. So obviously the exact numbers really heavily depend upon what exactly it is you're doing, or you implementing it at quality of service and things like that. But ballpark, about 50% of it is the I/O, and maybe 50% is just talking to these DRAMs, doing this network processing, doing these huge crossbars, and so on and so forth.
But is it a function of the distance you travel?
Yeah, so it's absolutely a function of the distance you travel. Now, as we'll see kind of by the end of the class, it's, at least so far, if I really asked you what was the cost of how many picojoules per bit does it take you per meter of distance, that answer is, let's say, highly nonlinear, okay? Because, and actually, oh, not there. Okay, so in like 2 more slides, I'll maybe say a little bit more about that. But basically, distance actually comes in a very, let's say, interesting way in terms of how it affects the things that we'll end up building. Okay, so I'll actually, again, remind me if I haven't answered it in a couple more slides. Okay? Okay, so I talked a lot about routers, but that's not really the end of the story. As I mentioned before, these links sort of show up all over the place. And if you don't believe me, I basically gave you another sort of alphabet soup of different links that you may actually pop into, all of which have these very, very high throughput and very stringent power requirements. So, in chip-to-chip signaling, here I just sort of took a picture of a couple of chips inside the PlayStation 3. If I wanted to talk between memories or even just talk between 2 processors, got to make sure I can do that, again, with sufficient throughput. We talked a bit about sort of these board-to-board types of things. So if you think about like computers or peripherals, it used to be that you had that good old PCI bus, which was running at like, originally about 66 megahertz, and slowly made its way up to about 400 megahertz. And then became PCI Express, which went up to, which started about 2.5 gig and is now sort of, I think, just starting to get into about 10 gigabits. That's PCI Express 3.0. In fact, if you look at USB, again, stuff you use those cables for, started out at about 10 megabits per second. USB 2 then got us to about 400 megabits per second. Next step, 10 gig. Okay? So that's USB 3.0. And, that's now we're talking about a meter or so of these cable kinds of things. Okay? And of course, people still want to keep going because, you can imagine as long as I've got more computing stuff or more, let's say, digital information that I want to get, I probably want faster and faster throughput over that same cable. Okay? So kind of the bottom line here is really we basically have this constant desire to signal faster and faster, but at the same or even lower power consumption as we used to before. Okay? And that's kind of universally true no matter where these links end up popping up. Okay? So given that context, I wanted to sort of come back to this, let's say, very cartoon picture and ask the question of, well, okay, so fine, I want these really high-speed links. They have to, do inside of these backplanes or inside of these boards or whatever. So what's wrong with this picture that I drew here? Why is it that I can't just have an inverter driving a wire and another inverter receiving it, and a couple of flip-flops on the two sides to just retime things? Well, turns out in principle, this really is a link. Okay, so in principle, nothing is wrong with the picture I drew here. But there's some, let's say, pretty important caveats. Okay, so the first important caveat is that this really only works as long as the wire is quote-unquote short enough. Okay? Now I'm going to say a little bit more about what I mean by short enough in 1 second. But for now, let's just take that as, let's say, something to think about. Okay? The other thing that's actually going to turn out to be really important, and we'll spend a good chunk of the class talking about, is this is all fine and dandy as long as you can get the right clock on both sides of the link. Okay? And what I mean by right, again, we'll actually go through in terms of the class, and you'll understand what I really mean by that. Okay? So kind of really there's these sort of two key, let's say, questions that I'm bringing up here. So the first is, when is that wire short enough that I can basically just sort of ignore it and just do some really simple stuff and get this thing to work? And how do I get the right clocks on both sides of this link? Okay, because remember, this is perhaps some chip sitting in, I don't know, Arkansas, and this could be some other chip sitting in, I don't know, Wisconsin or whatever it is, and clearly they don't know anything about what their clocks are relative to each other. And this wire, as you can imagine, may not be so simple as just me drawing a line on my circuit schematic and assuming that it's equal potential. Okay? So what this is really kind of getting at is that there's sort of two core pieces as to what a link really needs to do. The first is what's called signaling. In other words, it's literally just physically getting bits from point A to point B. Okay? And if you took 240, this is kind of actually what we spent a lot of the time focusing on. That was sort of just, what was the voltage or what was the, let's say, physical quantity that we sent from point A to point B. The other piece, which turns out to actually be equally important, in fact, maybe even more important as you really start pushing on these very high data rates, is figuring out which bit is actually which. Okay? Because like I said, if I'm talking from a chip in Arkansas to Wisconsin, they don't know squat about which clock is which or which bit is which. So you somehow have to figure out when is it that I should actually look at the voltage that's been sent to me and decide whether or not that bit was a 1 or a 0, or in fact, I could even do more complicated things like sending multiple levels of information. Okay? So kind of, I wanted to bring this up now because what you'll see when you go and sort of take a look at the syllabus is the class is really sort of broken up into kind of this introductory section where we'll talk a lot about the sort of basic issues and what the system looks like. And then almost the entire rest of the class will sort of be split into signaling, meaning how do you really do this in the right way? How do you get the physical information from point A to point B? And the other half will be really about timing, which is how do you figure out when is the right time to essentially decide whether a bit is a 1 or a 0. Okay? Okay, so now I think we're going to finally get back to Ricky and Linkai's questions from before. So basically, as I said before, conceptually, that very basic picture of, just having some flops and an inverter, okay, again, it's not exactly right, but conceptually it actually turned out to work reasonably well up until relatively recently. Okay, so other than the fact that just realizing those wires, there was the speed of light thing, and so they were actually transmission lines, other than kind of realizing that that was actually sort of how things behave, which drove obviously a few changes in terms of how people built the links, turns out that up to about 2 to 3 gigabits per second or so, life was actually pretty good for link designers. Okay, so basically, the connection in between, the thing that I've called the wire, which I'll sometimes refer to as the channel, okay, which is how it's referred to here, pretty much didn't do a whole lot to us. Okay, so back if you looked maybe 10, 15 years ago or so, in the quote-unquote good old days, link design was really all about just building fast circuits. Okay, so people wanted to take 0.5 micron technologies and figure out, okay, how do I do 2, 3, 4 gigabits per second of throughput? And this thing was a pretty slow technology. Okay, so if you looked at kind of a lot of the initial publications, a lot of them were just about how do I build really fast circuits that get very, very short bit times, and also just a little bit on kind of, well, how do I time those circuits and really decide what the right bit is, or decide what the right time is to look at those bits. Okay, so like I said, this was kind of the good old days, but the bad news is that now that picture is not quite so nice. Okay, so the big difference you should sort of notice between this picture and this picture right here is, on this one, this was kind of a representation of the signal that I sent at the transmitter. For those of you guys who have seen it before, this was like the eye diagram at the transmitter. If you haven't seen eye diagrams before, don't worry, I'll explain what they are next lecture. But kind of the key message is you can see these nice clean-looking things that I sent at the transmitter. Well, I got those same nice clean-looking things at the receiver. Well, now these days, if this is what you sent, this horrible, disgusting mess, which you can hardly tell what it is really what you'd receive at the input of the receiver. Okay? So that's really how the signal would look if you were to go at about maybe 10-ish gigabits per second, maybe even a little bit less than that. Okay? So what that basically means is that, we as link designers, as let's say electronics people, have to figure out how in the heck do you decide what the bits actually were, given that I have this huge garbled mess coming into my receiver. Okay? Now, as we'll see, that's actually going to drive a lot of, let's say, what the innovations have been over the last several years in terms of how you really build these links. Okay? And as I've kind of hinted at here, this is really all driven by the fact that you really don't want to be changing that backplane. Okay? Because it turns out, building that thing and installing it and, getting it maintained and all that, that's a lot of dollars. Okay? So as long as you can come up with, your nice new small little chip that somehow magically burns the same power as it did before, then actually it's a lot cheaper for you to just replace that one chip than it is to go and sort of redo the entire backplane design. Okay? Now, that's not to say that there aren't actually tricks you can play to improve the sort of, let's say, signaling quality or the signal quality you get on the other side. It just turns out they tend to be a lot more expensive, or at least in the past they've been a lot more expensive, than simply doing a better job on the circuit design. Okay? And if you don't believe me, there's been this very long and, let's say, heated debate about, okay, well, when are electrical links going to be replaced by optical links? And by the way, the only difference between electrical and optical, as I said before, optical is just electrical with junk bolted onto it. Well, the reason I say that is because, you just have to sort of get into the optical domain in order to make that link. Okay? But the only nice thing is that once you're in the optical domain, what you send really is basically what you see on the other side, at least for any reasonable distance, so to speak. Okay? So kind of the take-home message here is, again, that even though this looks pretty nasty and you can imagine is going to make life a lot more complicated from the standpoint of how we build the link, it's really the electronics that typically have to bear the burden of dealing with all of these, let's say, screw-ups induced by the environment. Okay? So just to make, let's say, life even a little bit more fun, turns out that, as Linkai was asking before, what's kind of, like, say, the typical power breakdown? Well, obviously it depends on the exact application. But just as an example, if I was to look at, let's say the embedded processor that may be sitting on your iPhone, well, you want that processor there because, you actually want it to do something, like you actually want it to compute something, right? So usually if you kind of look at how much power was budgeted to actually doing the IOs, it's usually only on the order of 5 or 10% or so, okay? So that really means that, you really have to get these kind of throughputs. You have to get these very high speeds over these really, really nasty channel conditions, all within a pretty tight power and area budget. Okay? Oh, and by the way, like I'm sort of showing on this picture, this, by the way, is the cell processor. These blue things, those are actually the IOs. That entire rest of the thing right there, which, by the way, dissipates about 100 watts or so, that's all some big, nasty digital block that's, likes to do whatever the heck it likes to do and creates, a couple hundred millivolts of noise on the supply, can easily create volts of, common mode variation between, different points on the board, and so on and so forth. Okay? So the message here is that, it is actually a pretty tough thing to do. And as I guess I mentioned a little bit before, indeed, if I get faster transistors, that helps. But unfortunately, because of this big beast and the way things scale for the digital logic, transistors actually aren't getting all that much faster. They may be getting a little bit faster, but certainly not like they used to be. But nonetheless, if I want to get more information in and out of here, I still have to meet that throughput requirement, because if I don't, the whole sort of, let's say, the whole system falls apart, right? I can't, keep selling you that new iPhone 5 or 6 or 7 or whatever the heck it is, okay? So the message here, of course, was not that, this is all about doom and gloom. This is really just to say that this is actually a pretty interesting area for us to be looking at, because there really are a lot of challenges here. But anytime that there's a lot of challenges, that also means there's a lot of opportunities for us to basically come in and do some really clever and innovative stuff to solve those problems. And in particular here, because we're dealing with kind of these large systems, there's actually quite a bit of interdisciplinary or multidisciplinary, let's say, opportunities. So, as I said, we're going to talk a lot about circuits. But turns out if you know a bit about, some communications ideas, that can actually go a really long way to basically cleaning up these really nasty, looking signals that I'm receiving or that I may even be transmitting in the first place, okay? Similarly, in fact, if I know a little bit about just sort of how to do some optimization, again, I can actually go a pretty long way. In fact, if I even know a little bit of just sort of electromagnetics, and I can think about, well, okay, how could I maybe just arrange this backplane in a slightly different way? You'll see that actually can have a pretty big impact on sort of the quality of the signals that you get, and therefore, of course, how efficient you can really make your circuitry. Okay? So kind of the sort of the take-home message here is that, at least in my opinion, what I think we'll really be doing in this class is learning how to build at least one of the most efficient communication systems that is out there in existence. And just to sort of give you some numbers to back that up, the best designs today are dissipating only on the order of about 0.5 to 2 milliwatts per gigabit per second of throughput. Okay? So just maybe to put that into the context, anybody know what, let's say, your typical even Wi-Fi transceiver, how much power would that actually take? Does anybody know? Anybody, looked one of those things up? And if you don't know, give me a ballpark. Yeah.
Like a few hundred milliwatts?
Yeah, it's a few hundred milliwatts. It's actually probably about half a watt or so. Okay, so what's the throughput they claim to give you? I'm not saying that's what we actually get. What do they claim to give you, let's say, in the most aggressive case these days? What does 802.11n do?
50 megabits or something like that.
Okay, so 50 megabits is like 802.11g. What do the N guys claim that you can get? I don't know under what scenario they actually measured this, but what do they at least claim that you can get? Nobody has an 802.11n? I guess we need to buy you guys new laptops, huh?
100?
Yeah, so they claim up to about 400 megabits per second. Okay, so if I'm doing, and let's say write this down maybe just to help you guys out. So if I'm doing about half a watt and let's even be generous. Let's even call that 500 megabits per second, which is half a gigabit per second. How many picojoules per bit is that? Or let's say even do it a different way. How many milliwatts per gigabit per second is that? Is it 1,000?
Yeah.
Oh yeah, actually you're right. Yeah, it's about 1,000 milliwatts per gigabit per second. Okay, in other words, for those of you guys who like energy per bit, that's about a nanojoule per bit. Okay, so 3 orders of magnitude difference. Now, actually, just to make our life even, let's say, more fun, anybody know what a typical cellular transceiver will take? How much output power? Forget even the transceiver. How about the PA? How much output power does the PA have to do? By PA, I mean power amplifier.
1 watt.
Yeah, it's actually about more like 3, by the way. So, if you looked at like GSM under the worst case conditions, they want about 3 watts or so. What's the data rate you get? Ballpark.
10 Mbps or something?
Yeah, about 10 megabits per second. Again, if you're kind of good, you're standing right next to the cell tower, and you shove your phone right next to it, right? Okay, so I won't even calculate that. You can imagine that's pretty bad. Now, to be fair, the distance here is very different, right? The channel is very different. In fact, the issues you have to deal with are also quite different. Okay, so now the point of this was not to say that wireless guys are bad and links guys are good. The point here was only to say that indeed, there was actually some pretty clever stuff that people came up with to try and make this work. Okay, now maybe actually just to prove that, anybody know what a 10 gig Ethernet transceiver? Anybody sort of looked, or even actually 1 gig? Anybody have an idea of how much power those things take? Nobody's looked at that, huh? Okay, so, well, why don't we do this? Let's take a guess. Anybody have a guess? Come on, order of magnitude. 100 watts, 10 watts, 1 watt, 1 milliwatt.
10 milliwatt.
10 mil. Oh, wow. Okay, so if you can build this, we should talk. Because I definitely want talks in the company. Okay, so based on that, obviously, which direction is it going to go? Okay, 100. Again, I still want stock in that company. Any other guesses? I've got plenty of, well, I don't have plenty of money, but I have plenty of something to invest. So, if people want to take more guesses, go for it.
10 watts.
Yeah, okay, so it turns out it's typically about 5 to 10 watts or so. Okay, so 10 gig Ethernet, this is a wired standard now, so this is, a link. Okay, so again, that's not to say that, just links guys are always great and wireless people suck. You can do bad things, or you can do, you can do good and bad things, obviously, in both. But this is kind of telling you that there's this very nonlinear trade-off in terms of, well, okay, why is it that, for example, 10 gig Ethernet is like this 5 or 10 watt kind of thing, whereas, my link that's just talking from let's say my processor to my memory, or in fact, even like on these backplanes, is maybe only this, 10 to 20 to 100-ish milliwatt kind of thing, okay? And a lot of it really, as you'll see as we go on, just has to do with complexity, okay? Complexity and really just understanding really what's going on with your channel, and then optimizing things so that you can really get the best energy efficiency you can, okay? So that's kind of, that was kind of, let's say, my high-level sales pitch as to why I hope to convince you that this should be an interesting class to take, because, if you really learn how to do this, then, I think these techniques that you'll learn will actually be very broadly applicable. So even if you're not going to end up building a link as part of your career, actually a lot of the ideas we'll learn will really be very, very useful in all kinds of other contexts. So even if you're working on RF kinds of things, turns out a lot of the similar ideas apply. You're working on, let's say, biosensors, well, guess what? There's a lot of mixed signal stuff that actually is pretty useful. Let's say you're working on data converters, well, again, a lot of these same ideas will really be very directly applicable, okay? So that's kind of enough of me giving the sales pitch. Now I'll just tell you a little bit about what we'll actually do. So the first thing we'll sort of start out with, maybe in 1 or 2 kind of lectures is kind of just, well, what is the link environment? What does this thing really look like? So I kind of gave you a little bit of an idea of that already, but I actually want to spend a little bit more time on actually diving into the details of, well, what goes inside of those backplanes and what kind of transmission lines are there and why is it that the channel looks so crappy at these very high data rates, okay? I'll also talk a little bit about, kind of towards the end of that, let's say, section of just, okay, how do you go about actually evaluating the performance of a given link? Turns out that's actually nowhere near as straightforward of a question as you may think. Because, as you can imagine, this is a pretty big, complicated system. And so lots of things interact with each other. In fact, there was actually a lot of work done just on figuring out what's the right sort of methodology to use to evaluate whether or not your link is going to work in a given context. Okay? So once we've kind of gotten, let's say the introductory stuff out of the way, that's when we'll really dive into sort of these core pieces of, this, first of all, the signaling, which again is really physically how do you get bits from one side to the other. So we'll talk about sort of transmitter and receiver circuits. We'll then talk about equalizer types, and actually we'll talk a lot about how you build those equalizers. And equalizers obviously is just how you deal with these bad channels. And then we'll actually also talk a lot about basically the bad news is that, I can build one thing and I can target it for one very, channel that I know exactly what it looks like, and I can build, the perfect implementation for that. But guess what? There's a wire right next to it that looks completely different. Okay? So that means you really have to know sort of how are you going to build these algorithms, how are you going to build the circuits that allow you to adapt to these widely varying conditions. And I'm actually going to spend a reasonable amount of time on that because it turns out if you kind of ignore that, you can build things that look absolutely beautiful but are completely bogus because they'd never be useful. Okay? So we'll spend quite a bit of time on that. The other big chunk to the class will again be on some of these timing circuits, or timing actually architectures and circuits. So we'll talk a bit about sort of what are the different types of links and what are the different types of clocking you might come across. We'll talk about how you actually figure out what the right clock is on the receive side. That's usually called clock and data recovery. And we'll also actually spend quite a bit of time going into the details of how you really build the circuits that make up these things. Because as I said, if you really think about kind of pushing the limits in terms of the performance, a lot of times it may not even be the signaling that drives your decisions. It may actually be the clocking that drives your decisions. Okay, so definitely important for us to understand kind of what's going on there. I will also talk a little bit about these so-called supporting functions, just because in the two in particular that I've highlighted here, I think are things that you're definitely going to run across, specifically in the context of links, but in fact, even more generally, if you just start looking at building complex and interesting mixed signal systems. Okay, so the first is, I'll talk maybe a lecture or two about supply regulation, because as I mentioned before, unfortunately, you're always going to have to build these things, kind of surrounded by a sea of a bunch of junk that could very easily destroy all the signals you're interested in. And then the other thing that I'll spend a little bit of time on, which is, maybe not, let's say, your standard circuits material, is how in the world you actually verify that this thing that you're going to build, this chip that you're building, is actually going to work when you get it back. Okay, so we'll talk a bit about how you really do some mixed signal verification. Okay, because I've actually personally worked on multiple chips where things like, digital buses were inverted or flipped, or there was hold times and just really, really stupid errors that cost literally man-years of effort just to go down the drain. Okay, so turns out there's actually some pretty nice things we can do here that turns out are not even that mathematically sophisticated, but are just very easy for you to go and implement, that I'm actually going to force you to do in the project, because otherwise I won't believe that what you did actually works. And by the way, even in terms of the project, like, you're going to want to do some of this verification kind of stuff, which will turn out to just be building behavioral models. Because if you don't do that first, you're really not going to have any idea of whether or not the whole thing you're working on has any hope of behaving the way you want it to. Okay? So that's kind of where the core material will be. And then, I actually left a reasonable amount of time for sort of, let's say, advanced topics towards the end. So if you look at the schedule that's up on the web right now, I think I've got about 4 or 5 lectures of so-called advanced topics. My expectation is that some of these other things will take longer than I may have planned for. So there's sort of some slip room there. But if we have time, then we'll talk about some of these more advanced things. So let's say more advanced communication techniques, other types of channels, other types of actually sort of, let's say, link architectures you could think of, and things like that. Okay, so any questions on that, or in general on the class? Yeah?
Project, you mentioned that you should build the entire link.
Yep.
So does it include, for example, PLS to generate the reference clock? And the second one is that, we should use some kind of technology. So do you have any idea?
Yeah, so the questions were basically about, I said you're going to build the whole link, so does that mean you're going to build the PLL, or basically the clock generation circuitry? Absolutely. Okay? So, by the way, there's a reason why I have, 4 or 5 weeks of lectures on timing stuff. Okay, I like to talk, but, I like to see you guys actually do the stuff too. Okay, so you will definitely be building a PLL. In fact, you'll be building phase interpolators, you're building clock and data recovery, you'll be building adaptive equalization. So, like I said, you're going to build a complete link. Now, that's not to say that I want you sitting there, building standard cells and, doing the layout and things like that. I'm going to try and make this sort of, so that we'll focus on, let's say, the most relevant pieces from a learning standpoint. So that's also why I said it'd be good if you have somebody who knows Verilog or VHDL, so you can actually code a lot of the back end kind of stuff. But the core circuitry, I want, let's say, my goal is to really actually have people build the entire thing. We'll see how that goes. If I find out that, okay, nobody's actually even getting close, I'll throw you some behavioral models or something like that, and we'll kind of go from there. But my goal really is to kind of put the whole thing together. Okay, so that's why I said, several slides back, this class is not going to be just, a fun class. Like, well, okay, it will be fun, but it won't just be, you partying or whatever. Like, there'll be a lot of hard work here. Okay, and so, again, pick your group wisely, because, having somebody who knows something about PLLs and somebody who knows something about, let's say digital back-end stuff, and somebody who knows about, equalization and stuff, all of those skills will definitely be useful. The other one was, you asked about which technology we'll use. I think I'll probably be using sort of a 45 nanometer predictive technology. So performance-wise, you shouldn't have too much of an issue in terms of just raw transistor speed hitting the 10 gigabits per second. So I may tweak the model a little bit sort of to make that true. But that's kind of roughly what I'm thinking of targeting. And I'll also try and make it so that, again, there'll be things like standard cells, or give you some sort of base, initial designs to start from to maybe just reduce some of the grunt work that you'd end up doing. Other questions on the class, or? All right, great. Oh, yeah.
Is the design all the way through layout?
No. So there won't be any layout unless you really want it. No, so I don't think we'll be doing any layout, not because that's not important. It actually does turn out to be very important. But simply just, I have to limit the scope somewhere because, obviously I don't want you guys just slotting yourselves completely. There are some things to be learned about there, and where it's relevant, I will talk about that, when we talk about the circuit details. And so I may actually ask you to do things like, pretty detailed floor plans and stuff like that. But I won't take it to the level of you, pushing polygons and, spending nights dreaming about, poly and metal and etc. There is, I guess, a limit on my cruelty, so to speak. Okay, so unless there's any other questions, I'll see you guys on Thursday. You can just ask me offline.
Okay.